to when we left my assessment, majority of you have already created the Mastercam files with the toolpath added. Before November 1st, I received three submissions. I will name them Ryan, Joe Nugent, and Tan Wu. And yesterday I received one more from Omer. This is not the report that I was asking for. We got a legwork to do. When I say we, myself and Dave. Dave will not be returning till the end of this week. He's sick. But I can evaluate. So what I asked for by tomorrow is your Mastercam files, which most of you would have been very, very close. Okay. So I am going to extend that deadline to Friday 5 p.m. when I would request you to give me the files so that I can move on it, evaluate before it is cut. Now, the university has been suggesting several scenarios. I am not sure whether they know what they're doing. At this point in time, classes will go on till the end of this week for courses that continued during the strike. In mechanical engineering, only one stupid guy like me stood outside. So you may not see much of an impact in mechanical except some service courses. Okay. I don't think civil or bio matters at all. Nobody probably moved. Electrical will be affected. So I am told, as per the last scenario, the classes that were not held will carry on till December. I'm pulling by the calendar. Till 24th of December. That means I have 3 weeks. I'm behind as a result of the strike by 5 weeks. Okay. And then they say the classes resume on January 3rd or 4th. I'm not sure. I have not checked. And go on till 17th, giving us another 2 weeks to wrap up the course. So everything is doable. Nothing will be sacrificed. Some adjustments have to be made, which I am willing. I do care about the students. Otherwise, I wouldn't be here. So I don't want to sacrifice on what you might be learning through this course. So everything will go on as usual. So I also checked with Trevor. I've been in the building very often because my picket line was very close to engineering building. And yesterday he told me that all the software links, everything is working. People have been signing into it. There has been no issue at all, according to him. And he showed it to me in his office that everything is accessible. So that should not be a major deterrent. Now, what I am going to do, I will keep the projects intact. The term test 2, 10%. The time has gone by. It was sometime around November 24th or whatever that I posted. I would do this only after you come back. Okay, then there is a final exam. So nothing would change as far as I'm concerned. It's unless I hit into some roadblocks somewhere. I spoke to the head of mechanical yesterday. and told him it is up to them, not me, who should be doing all the rescheduling of things. Okay, so right now I'm going to follow what has been put on the web by the university, not by the department or not by me. The D2L was never pulled down by me or by any staff prof in charge. It was done by the university, not by us. But I checked and it's all intact now. So that's about it in regards to the course carrying forward. Any questions on this? Anybody? No? Okay.
So I have a
Yes?
question.
Yep.
How are we gonna get 5 weeks worth of work done in 3 weeks or 2 weeks?
No. You have 5 weeks. You are going from now till 24th of December, according to the university.
Okay,
Okay.
so we still have all the time we lost.
Yeah. Till 24th, the classes will be going on in courses that were suspended, not
Okay.
other courses. If some of the profs carried on during the not lockdown, during the strike, those courses should end by this week. The original closure of the term 1 was December, the end of this week. Okay, so if you are doing some capstone, whatever, it should all be over, okay, by this week. Then in mechanical, my course will move on. I don't know what are the other service courses that are affected. Maybe some from math. That I have no knowledge, okay, of those courses that are affected. We should move on till 24th, according to the university. Okay, so the last day of class will be 24th, and if it happens to be a Friday, obviously you will finish on 23rd. Okay? Then when we come back, starting 3rd or 4th, I'm not sure the exact date, we carry on for 2 weeks. And then they say the exams will be concluded between 16th to 19th, and term 2 starts on January 19th. So those of you who are registered in SEMA 2, at this point I see only 2, will be in person course starting January. That's the university's rule. Okay, so nothing would be affected. Presumably, the midterm break will be shortened to 1 day in term 2. That way they gain 1 more week, and then maybe the term will finish 1 week late than the normal. That's what I have been seeing on the web, with not much of a clarity on some of the issues. Okay. So, did I answer your question?
Yes, thank you. Also I was wondering if I can speak with you at the end of this
Yes,
one.
yes,
Okay,
you can.
sounds good.
Okay.
Thanks.
If there is no further question,
Actually, a quick question, Professor. Um, have you have a date in mind for the second term test? I believe you're muted. Sorry, we can't hear you.
now can you hear?
Perfect.
Okay. I'm waiting for what the scenario 5 finally will turn out to be. Is it a 4th, 3rd, whatever that we start? Then I would hold a term test. I have enough material for term test 2. In the first week, I would look at the calendar. I will tell you on Thursday class. when the tentative date for the term test would be. The final exam, I don't control. The university is going to control it. Okay, so that's what it is at this point, but I will confirm on Thursday. Right? Clear?
Thank you.
Okay. Now, this afternoon, I'm going to move on with project number 3. Project number 3 and 4 will be linked very solid. Okay, but I will present project number 3 first. You can work on it during the break or whatever. It's not due until you come back, because we do have to test, you do have to link. The software that is required is WinLoader. But when I present the project, you don't go into the software at all. There is the modeling that is required, that you can, it's going to be paper and pencils to start with before you get to the actual software, and then implement it to test it on the model. Okay. So I have not spoken to Matt. I do not know what the situation would be for him to continue to be a TA, because he has to be paid. Something the faculty should take care of. As far as I am concerned, I don't give a damn. I'm not paid in terms of the last days. But I do worry about many younger people who stood in the line. Okay? I stood for the sake of those people, not for myself. Anyway, we'll resolve it. I will speak to the head and possibly to the dean through him. We'll see what happens. But whether Matt is there or not, I can manage all of it, except I have to do more work. But I am game for it. Okay, so if there are no further questions on this, I'm going to close the screen and move on. Now, you should be seeing the screen. Let me do it. Okay, do you see my PowerPoint screen? Give me 1 minute. Okay, do you see PowerPoint screen?
We can see it, but there's a box in the middle of the screen.
Box in the middle of the screen.
Yeah, that's good now, I think.
Okay, let me go where I stopped. The notes for this was already posted and should be there. So end of 12. Okay. So I'm going to revisit, because I'd already crossed the slide, but I'm going to start this case study from scratch. So what we have is a furnace. The role of the furnace is to basically prepare blocks of steel, whatever, for forging. So it has to preheat to a certain level before the forging block is removed and goes through the next stage. At this point, we are not worried about the next stage. We are only worried about the furnace that is preheating the forging block. So how does the furnace heat up? Obviously, there has to be a heat source. So in this case, assume there is a natural gas heater which is present inside the furnace. So if the natural gas system has to be on or fired, you need the natural gas to be supplied to the head of this flame unit by opening a valve or shutting the valve. Opening the valve will allow full flow. We are not talking about reducing the flow or controlling the flow. Either it is on or off. So binary 1 or a 0. When the valve is opened, obviously the gas is going to flow, but it's not going to ignite. You have to ignite the flame, rather the gas. So assume there's some kind of an electronic ignition which comes on when the valve is opened. No time delay. It comes right away. Okay? So when the ignition system comes on, it will attempt to light the flame. There is a good chance on the first stroke itself, the flame comes up, or maybe there is a time lag, maybe taking 2 tries, 3 tries, 4 tries, who knows, depending on conditions. But eventually, either the flame comes on or does not come on. So you do not want to be letting the gas go into the chamber if there is no flame. So assume there is something that is monitoring whether the flame comes up or not. If the flame comes up within a period of time, so there is a period of time that would be specified to the control module. In this case, if the flame does not come up for 5 seconds while the ignition system is trying to get the flame going, shut down. When I say shut down, the gas valve must immediately close. Okay? When the gas valve closes, obviously the ignition system has no more role and it also goes down. So as is stated in the last bullet on the slide, let me see whether I can get my pen going. There is a timer involved. Okay, that's the conclusion you can make at this point. Now, it's a very simple problem. Excuse me. The simple problem can be made complicated or made more comprehensive by adding more bells and whistles. For example, you don't want to start the furnace until you're ready. Okay? And you don't want to have the furnace go on without nothing inside. So you need to load a forging block. Now, if you need to load the forging block, you have to have a sensor to detect whether there is a forging block present or not. Also, there must be some kind of a door that is isolating the inside of the furnace to the exterior. So when you want to load, the door must open, and when you put the block inside, the door must close. So there are all kinds of other things that can be added. You can also bring in proportional control into the picture. Okay, what is this block made of? Is it aluminum? Is it steel? Is it brass or whatever material? You may be having to heat them to different temperatures. So maybe you have to control the intensity of the flame inside. So the problem, as I say, can be in real world, not can be, in the real world will lift up to a much more complex control module. Okay, right now I will stay with what I have stated. So the first step, like every other problem that we have seen before, you must identify the inputs and the outputs. So power must be applied to the system to move on. So the power is an input, which is a switch basically. If the switch is in the on position, it is 1. If it is in the off position, it is off. So the characteristic of the switch, like in every other example that I have gone through before, has two possible states, 1 or a 0, and also the type of the switch. Is it momentary on, or is it always on when you toggle it? Well, in this particular case, I'm going to assume if you flick the switch, it stays in the on position. If you flick the switch down, it goes to the off position. So either it is on all the way or it is off all the way. Then the flame. Assume there is some sensor, heat sensor, that is located somewhere to detect whether the flame has come up, which is 1 if it is present and 0 not present. At this point, we are not going to introduce any more inputs. As I said before, the door opening, closing, whether it is open, whether there is a block present, we cannot start adding more inputs. How about the outputs? The gas valve, which lets the gas go in. Let's assume the gas valve has only 2 positions, like your bulb valve present in to control water, right? So if the valve is in open position, it is assumed to be an output 1, and if it is in the shut position, it is 0, nothing intermediate. So G, which is the output, represents the gas valve. Then the ignition. It's an electronic ignition. Nobody puts a match inside and starts lighting up the flame. So electronic ignition comes on, activates sparking on the electrode. 1 if it is activated. 0 shut down. That means it's gone. Then remember, if the flame does not come on for 5 seconds, you shut down the system. So in this case, an alarm has to come on to indicate that all things are to be shut down. So when the alarm, could be a light, could be an alarm, like a siren. If it is on 1 and it says flash, that means it could be a blinking light. In our case, it is just on or off, and 0 not on. Okay. So those are the essential inputs and outputs. More can be added. Okay. Now, to approach this problem or any problem, first put the logical statements to see what should or how should the process be controlled. So the first logical statement is, well, start the ignition, which is the output. And then question, when should that ignition come on? In our case, well, power is a prereq. So when the power is applied and the valve opens, right away start the ignition system on, provided there is no flame. Now, looks a little quirky. No flame. Well, obviously, when you start the furnace for the first time, there will be no flame. So you start the furnace when there is no flame, and when the power is applied to start the process, the gas valve will open. Okay, and the ignition will start sparking away. The moment the flame comes on, shut the ignition system on. So no flame is the condition. Okay. Number 2, the gas valve, the fuel. Okay. Only 2 positions, open, close. Okay. So the control system must decide when to open and when to shut. Without putting the next step here, I can say this is what's going to happen. At the beginning, there is no fuel present, power is applied. So what should be the first thing happen? Gas valve should open, right? When the gas valve opens, the ignition must come on right away. Okay? So the decision to open or close happens at this stage. Now one may question, is it okay to get the spark going a few seconds earlier than the gas valve opening, or a few seconds later after the gas valve is open? These are all decisions that you make to suit a certain process. Okay? For example, if you take the internal combustion engines, when does the spark come on? Typically top dead center, when the piston is at the top position, fire away. That means the fuel is fully compressed. Some engines require it to be slightly ahead. So advance or retard control of the spark may be a little bit different. Now, some internal combustion engines have double spark, twin. That means one spark comes at the right time, another spark comes slightly a few milliseconds later to make sure the fuel is combusted fully. That means the efficiency increases. So there are variations that can be incorporated. That means the problem will change. Okay. Now, why is my slide not moving? Oh, okay. So the third prerequisite is power. Power is absolutely required for all of this. Now, here I am assuming the power is on when once you flick the switch and it stays on. The problem will become more complex if the power is a pulse input. That means I flick the switch, the command is sent to the controller, in this case a PLC, and after that the power switch can come down to a 0 position. That means off, but the pulse has been sent. The problem will change considerably. Okay, so in this case we are looking at power being on momentary and done. Sorry, the power is on continuously. Now we said 5 seconds. If all things don't go well, shut the system, and I'm going to give you a period of time. Okay, so a timer is coming into the picture. What is the role of the timer? When the gas valve is open, the timer kicks in and it is starting to count down from 5, 4, 3, 2, 1. The sensor keeps looking at it. The ignition system is sparking away. At the end of 5 seconds, no flame for some unknown reason. So the timer is going to play a role, and when the timer is expired, trigger an alarm to come on to alert the people that the furnace failed to ignite. Okay? That means the system must be shut down by the controller. Okay? So how would I approach this problem? First, the problem statement must be understood very clearly. Identify for whatever that is required the inputs and the outputs. Then put the logical statements. In this case, I have put 3 logical statements. There can be more, but this is the starting point. The next step is to do the timeline diagram, which we have done in my previous example. So in this case, you have the three outputs, the G and the S and the A, identified in red, and the two inputs, the power and the flame, P and an F. So with this we can do a timeline diagram. So the timeline diagram should basically reflect what should happen in the process if things are going right, as well as some idiosyncrasies in the process, which I will tell you very soon when I explain the timeline diagram. So what we have is at time this, which is 1 second, power was applied. So immediately gas valve is open. One may question, should it be that instantaneous? Well, these days systems are very, very responsive with a slight nanosecond delay. When the power is applied, gas valve will open. Okay, so what happens here? The S, which is the sparking, that also starts. So P, G, and an S are all starting at the same time. Well, did the flame come on? No, the flame has not come. Why? Well, there is some thermal lag. Maybe the flame unit is not that clean. Who knows? But we must analyze all possible scenarios. So no flame. Okay. Ignition is going, trying. Okay. Absolutely no flame, or at this point, just before the 5 seconds, the flame came on. So there was a time lag of 4 seconds. But fortunately, the flame bounced. So when the flame comes on, as is shown here, there is no role for the ignition anymore. It shuts down. So flame goes up, ignition comes down, right? All is good. Is the power still on? Yes, the power keeps on. When I say power keeps on, the switch is flicked. There is no motor, nothing to control that power switch. It's manual. All is well. Then, at this point, which is 9 seconds into the process, flame went down. Why? I don't know. You don't have to worry. We are analyzing from a control perspective. Of course, somebody should figure out why it went down. Okay, so what happened when the flame went down? The ignition immediately comes up because the gas valve is still open. This is the gas valve. It is still open. So ignition comes on, and after 1 second delay, flame comes up. Okay, this goes down. Gas valve is still open, so the flame is on. Then it keeps going. At this point in time, which is 13 seconds, flame goes up. No, flame goes down. Then ignition system or the sparking comes up. Okay, what does it do? 1, 2, 3, 4, 5 seconds. It is on. Okay, did the flame come up? No. Okay, is the gas valve open? Yes. At the end of 5 seconds, as a result of the timer, the ignition system goes down. At the same time, the gas valve goes down. And at the same time, the alarm comes up, alerting, well, catastrophic failure. 5 seconds, nothing happened. So, alarm comes up. Or how about the power? It continues to be on because alarm is on. Nothing is going to happen here if the control system figures it all out. Then somebody comes, pushes the power down. When the power goes down, the alarm shuts down. It's time to get into the system and fix the problems. Okay? Now, what is going on here? At the time 14 or 24 seconds after the power was shut down, suddenly the flame sensors say, hey, there is a flame present without gas valve being open, without ignition being open. How is that possible? Well, you have to analyze for all possible scenarios. This could happen. I don't know what might happen in the actual system. Residual gas and residual heat made a little explosion inside. Let's assume. So, but if this happened, none of this should come back and trigger, because there is a problem here inside the furnace. It went down and stayed. Magically, the flame appeared. Let's assume one explanation might be some residual gas present somewhere got ignited, and then it finished whatever that was inside. There is no more flame that can be sustained. No, system must take care of these possible scenarios. Okay, then what happens at 27? Okay, the power went down, somebody switched off, and somebody came back and assumed that everything is okay. It is time to start the process. They put their power on, gas valve was opened, spark was initiated. About flame? No flame. So system is not in good shape. Gas valve closes when the timer expires. The ignition closes. Power is still on. An alarm comes up, and somewhere behind what is hiding here is power goes down, and everything goes down. So timeline diagram tells you pictorially before you move on as to what are the possible scenarios or conditions that one should be looking at in order to model this system. Is this clear? Do you have any questions about the timeline diagram and the assumptions and the idiosyncrasies in one instance?
I have
Is
a
there-
question.
Yes.
So how come the second time the alarm goes on, how come it doesn't stay as long as the
Second
first
time, or what time interval are you talking about? Second time alarm comes on is here.
32 to 34.
Yeah. Okay. So what happens here is, why did the alarm come on? Okay.
Because
So,
there's flame, right?
the flame came on, right?
Yeah.
For unknown reason. No gas valve open, nothing, whatever. The flame came on. So this is a situation when there is no power. If the flame came on, the power is down. So nothing, no gas valve should open, and no ignition system should open. Okay. So nothing happened here. But at this point, I assumed that everything has been cleared and I'm trying to get the system back. So this came back, and for 5 seconds, no flame here. Just kept on going, trying. So at the end of 5 seconds, this collapsed, the alarm came on, right? It would have lasted forever if this power had been kept going. But what you probably, do you see on the screen the participants? It's underneath the participants. If I can move somewhere here, it goes down. Okay, so that's why the alarm goes down here.
So I understand why the alarm goes on. I'm
Mhm.
just wondering why it's not the same interval of time as the first time that it goes on.
Okay, because the power was killed. Okay, what is hiding behind? Let me move this out.
Oh, I see. Okay.
Yeah, by that participant list is masking it. The
Yeah.
power was pulled down right here to coincide with this. Oh, yeah, right here.
That makes sense.
Okay.
Thanks.
Anybody else with any other question? You should understand the timeline diagram perfectly because that helps you get into the problem much faster in any situation. Okay. And also make sure the timeline diagram does not represent only the good possibility. There is always things that can be messing in the system, as was the case right here. Okay. In this case, if it was an electrical motor that was coming on, one could question, well, how did the electric motor come on? There is no power. Well, in that case, it is a garbage situation. You're just creating to make sure that the logic that you're going to strike can also answer to those problems, right? It's something like on an elevator shaft. Even before pressing the button, and nobody is pressing the button, suddenly the motor started moving and going up, right? Why? Is that possible? Well, the only way you can explain is maybe there is a short on the cable and the switch got stuck in the closed position. Who knows? It has to be investigated. But the control system must lock all these possible scenarios. Another example that I would give. Okay. Now, if you put your finger on an open window on a car with the power window option, those motors are very powerful. Yeah, they can literally cause injury to your finger if you put the finger and you forgot and you keep pressing the button to close the window. Okay, it has happened to me. Okay, so is there a system that will stop it? Well, you have to have some kind of a torque sensor on the motor and set the threshold so that it stops even with a slight push on something softer. Why would people not do it, especially with the kids traveling in the car? It's going to cost money. Okay, so cutting corners, that option doesn't exist. Okay, the other example I would give, garage door. Okay, when it is closing and it is closing with the car present underneath, yes, it goes and hits the car, and if you had set the torque correct, it will bounce back and trigger the flashing light to say there is an alarm, right? So things like this must be taken care of in your timeline diagram. Well, I'm not going to look at this slide because I've already explained this in greater detail. Okay. Now let's go to the last two bullets here. Control system has to deal with three outputs in this case. Fuel, ignition, alarm. Okay. So we must now proceed, okay, to analyze each one of those states and see what needs to be done. You can go straight to the truth table analysis, which I will show you in the end, because now I am showing you the alternate form of analyzing the logic model for a process by going to the nitty-gritty of the logical assumptions. Even if you go straight to the truth table, you have to understand this procedure of putting the logical statements and coming up with statements. Your life will be a lot easier. If you go straight to the truth table, you will still be struggling. Okay, on row 7, what should I have as a G or an S or an A? What should happen? Either you can close your eye and put some zeros or ones, and then later on you find things are not right. Or go back to your logical statement from time to time while you're filling the truth table. Okay. So first, let's take the fuel. Okay. Fuel is the gas valve G. Okay, in this case, so the flame is F, the gas valve is G, and the gas valve is the one that's sending fuel in. What should be the requirement for the gas valve to open? First condition is the power. Second condition is the flame. That means if these two are present, the gas valve must remain open. That's the first condition. In this particular problem, there seems to be two possible solutions. And once you see the two possible solutions, you can immediately conclude there is an OR operation that's going to come through. Okay? If it is this condition and that condition, then you are going to conclude there is an AND. Okay? So right now, let's not go into those logical operations. Both the power and flame are on and the system is operating normally is one condition. What is the second condition? Power is on. Power is a prerequisite for everything. Ignition is pounding away, attempting to ignite the fuel. So for the ignition to get its full blast of try, you have to keep the gas valve open. Okay? For how long? Until the safe limit, in our say, let's assume 5 seconds, has not been exceeded. Okay? So that's the second. So this, I'm writing on this or this are the two conditions. Some of you probably are living in an apartment, some of you are living in a house. It is very unlikely apartments have natural gas fired range or an oven. It's usually electric. But in houses, some people prefer natural gas. That means you have to tap into your natural gas line. Now, the modern day natural gas ranges have a sparking system. If you turn the knob to the extreme first position, you will hear the click, 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 click with the ignition spark between a little ceramic head and the little opening on the your range unit, and hopefully you will get a ignition coming up. Now just remember, I keep telling my wife about this, we have a natural gas range. If in the case of the range, you have to open the valve to let the gas come through, and the ignition automatically starts firing away. When the ignition has done its job, it doesn't quit. Okay? It keeps firing away until you turn the knob slightly clockwise or counterclockwise, depending on how you see. That means you are manually turning off the ignition system when the flame is present. Also, there is no feedback if there is no flame that the ignition quits and the gas valve shuts. Everything is controlled manually by you. The danger is, let's assume the gas valve is opened on this range and the gas is flowing through your burner. The ignition sparking is coming, but either the sparking unit is not clean or your burner surface is not clean, flame is not coming, but gas is still flowing. You're filling your house with natural gas, unburnt. That's not bad. It's a leak for a short time. But what happens if you had some other spark that comes up? Maybe you accidentally light a match because you think the ignition system is not doing the job. You will have a good combustion that would take place depending on the amount of gas, unburnt gas that has accumulated right above your range. Okay? Safety is not there. But again, to put that system, it is going to cost more. It is possible to motorize your gas valve or your dial, but how much more money? It'll cost you much more. So people don't do it. Okay? So now let's take this first two possibilities. Can we come up with a block symbolic representation of what might happen on this system? So I have identified here what should be controlled as output: fuel, ignition, alarm. And I don't know. I know that the first condition for the fuel from my previous slide, there has to be an R. Output from the R goes straight to the fuel. But right now I don't know what these inputs are. So I put a question mark. Here I have got the two inputs in this process. The only two that are being considered, which is the power and the flame. Okay, so what's here must be decided. Now we are looking at one output. We have another one to deal with and a third one to deal with just these two. So whatever that is here is going to come from your analysis or whatever analysis I'm going to present. Okay. The next slide. Both the power and flame must be present to achieve the first condition for fuel. That's the very first logical statement. Power and flame, both must be present. So both are going into this AND operation. If these two are true, if this is one, I get one. If one of them is not one, I will not get one here. So I know that is an input to one of the inputs to this OR gate. Now this is a question mark. So what is the second condition? So both and must suggest the use of R and for the operation of P and F. The other do you see something blocking the PowerPoint slide? I gotta move this out. Okay. Two other alternatives for fuel on. Sorry, not two other, the other alternative. Okay. Three requirements: power, ignition, and timer not expired. Power is already an input. Ignition, attempting to light flame, but no flame yet. What is ignition? The sparking system. Time. What is that block? It's the time that you decide as to what would be the safe limit before the alarm comes on. In my example, I am assuming 5 seconds, right? It can be anything. Okay. So power, ignition, and time all must be present. And in this case, since there are three, a 3-input AND connected to what? Input P, inverted NOT flame. That means flame not being present. That means a flame through a NOT operation. And an inverted NOT output from a 5-second timer. These are the conclusions or what you are going to decide based on this condition, where there are three things that should happen. Okay, so using that information, we completed this operation. Okay, so fuel is controlled by one of these, either this or this needs to be present. So if I had 1, I get 1, 1, 1, 1, I get 1. Fuel gas valve would have opened. Okay, now this is what we are going to now use to put the other input for the this R circuits that's controlling the fuel. Power is required. Let's assume it is 1. Okay, because I showed it as 1. Now flame. Okay, let's assume the flame is here as 1, is 1, this is 0, this is 0. Okay, what will happen now? If this is 1 and a 0, obviously this will become a 0. No matter what happens to this input. The AND requires all 3 inputs to be 1, right? In this case, I'm not even considering this last section. Boom. Power is in, flame is in. Now, is there what should happen to the output here? 1 and a 0 through this NOT becomes a 0, but this will keep the fuel going. No matter what happens to this, this has become a 0, right? So the fuel will continue to play its role because the flame is on, power is on. Now what happens if this becomes a 0? Flame died. This is a 0. This is a 0. This becomes a 1. Inverted 0 is 1. This becomes 1. 1, 1. Should this become a 1? No, we don't know what is happening. We have to analyze the last input. So the last input is now going to control what should happen, right? So flame is down. Should the fuel be open? Well, remember, you don't immediately close the fuel. You bring the ignition system back. It has to do its job to get the flame going. So this is now the last input is going to play a critical role. Okay, so let's assume, not assume, let's look at what is needed to complete the last step 3. Going back here, timer, and NOT operation is going here. The input to the timer is left incomplete, and we have to complete it. Okay, so we have to look at the logical statement to see what needs to be done. You need an input to the timer. It's left as a question mark. The way the timer has been portrayed to be working in this course material, the timer needs an input to be on continuously. For the timer to count down, let's say in this case I store a value of 5 seconds in the timer. and I apply power to the timer, click, 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 it's going to go down towards the 0. Okay. When it goes to 0, the output from the timer will be true. But output from the timer, if it has become true, will collapse if the input to the timer is also killed. That's the assumption we are making for the functioning of the timer. There are many variations of the timer. Okay, so let's look at the situation. I have a timer block here. I have an input, and the timer has got an output. Okay, so when let's say I store a time of 5 seconds, I became 1. What happens to the timer's output when I do this is a 0. Then this becomes 4, this becomes 3, it continues to be 0. When this becomes a 0, that means it has counted 5 seconds, this moves up to 1. And this output from a 0 will become a 1. Right? But if during the, let's say at the end of 3 seconds, I collapse this timer to a 0, of the timer to a 0, this will remain a 0. Okay. The second time it'll go back is when I re-switch this to 1. So at the end of 4 seconds or 3 seconds, I collapse. The timer resets to 5. It starts all over again. Okay. So you have to understand that's the assumption I'm making in this statement. If the timer is interrupted by off periods at intervals of less than 5 seconds, the timer output will never turn on. The assumption, again, if you make the assumption to be different, yes, it is possible, but it must be reflected in the PLC's logic. Some may support other assumptions, some may not support other assumptions. Your project number 3 is going to use all of this. Okay. The project number 3, the first phase, you are not going to be using any timer or counter. But project number 4, which extends the same problem to another level of complexity, will involve timer and a counter. Okay, so at this point, for project number 3, you are looking at no timer, no counter, brute logical gates being implemented into the model. Okay, you will see it this afternoon. So, if the flame appears before 5 seconds, we do not want the alarm to be activated. There is no need because things have stabilized and come back to shape. Okay, so if you take the timer, the time that we are going to be looking at is the period when power is on, but the flame is not present. I flick the power, and I'm assuming the flame is going to come on, and I'm going to start the timer. All is well. Flame came on before 5 seconds, no roll for the timer. All is not well. Up to 5 seconds, no flame came, and the timer started counting all the way to 0 seconds. Yes, it is going to play a role. Okay, so keeping that in mind, okay, we have to now look at the two possibilities connected to P, the power, and no flame, not F. Okay, so this and this states you are looking at an AND circuit. Okay, so we were here with the question mark on the previous slide. Now we are going to complete what is this. Okay. So P 1. Flame, let's assume 0 is 0. Output from this AND would be a 0. That means timer is not triggered, right? So here it will be a 0, here it will be a 0, here it will be a 1. Now P is 1, this is 1. What is going to happen here? Flame 0, 0, 1. It goes as 1 here. 1, 1, 1. Gas valve will be open. Why? No flame. Timer has not expired. Power is still on. You're allowing the gas valve to give the system a chance. Then P, or rather F, the flame, from a 0 became 1. Flame came on. What should happen to the gas valve? Yes, it should be open. Let's see whether it works. This becomes a 1. This becomes a 0. This becomes a 0. This becomes, this is 0. This is 1. This continues to be a 0. The timer's input is 0. The timer's output is 0. This is 0. This is 1. This is 1. Gas valve is kept going. It's the same condition as was before. So this part of the logic appears to work with my hand simulation. All that we have done is to solve one output. There are 2 more that are running, right? We've got to complete that. So let's do those 2, which is the last step. Complete the loop for S and A. Okay. Output S is identical to the second input for the R, which is controlling the gas valve. Output A is the timer output. Very simple. Now it's just moving in faster because you have solved everything pertaining to this, and this is a key. So whatever that is going here is going here, the same output. So this output is now feeding this and feeding this. The alarm comes right here. Okay, now the usual question that comes up in the minds of people is, if the power goes down, what happens to the timer? Okay, so power 1 is here. If the power is 1, this is 1. If it became a 0, this becomes a 0. This definitely becomes a 0 because even if one of the AND inputs. So the timer, okay, the input is 0. The timer's output is also a 0. And if this is 0, this becomes a 1. This is where some confusion happens in the minds of people. If the power goes down, how does the logic gate NOT still is functional? Or when the power goes down, the timer to bounce back to the 5 to restart, how does that happen? Remember, just like your computer, when you switch on, do you have to rekey your date, day, whatever at the beginning? No. It's got a non-volatile memory. And the non-volatile memory could be not needing any power from a digital logic perspective, or needing power. In the olden day computers or laptops, there used to be a tiny little lithium battery inside, which keeps your parameters intact, like the formatting of the hard disk, the clock, and so on. As long as that battery is good, you have no issue at all. But once the battery goes down, which is usually 5 years, suddenly one day your clock is not set right, your a hard disk is going crazy and it's asking for you to reset. Okay, so until you replace the battery, which means you rip open everything and look for the battery somewhere inside, nothing will come back. These days it has been handled with a non-volatile memory resident which you can reset. So assume that's what happens in the PLC control. A PLC, which you will see this afternoon, will keep the program intact even when the power is removed. Unlike the CNC machine that you was used for your project 1 will be used for project 2. When the power is killed, the resident program is gone. Okay, yeah, but parameters are not gone. The part program that you loaded for somebody is no longer there. You got to reload it, unless I throw your program into its memory, which is also possible. Okay, which we don't do because we don't want to keep loading memory with all kinds of programs and then worry about whose it is. Okay. Oh, that reminds me. When you get your project 1 evaluation, which I will send it away, one of the things that you have to pay attention to, some of the common problems that I have seen so far, everybody names their program as project 1, project 1, project 1, even though it is inside a folder. Remember I told you to somehow indicate somewhere your name. You can call it as project 1 Ryan, project 1 John, or whatever. Then it makes me distinguish one from the other. The other one, when you store your toolpath file, please store with the ISO view in play. Not just store random views, because when I open, sometimes I just see just the middle hole alone, because that's how you saved it. Then I have to go back and reset and so on. The third one is the depth of cuts. Some you're plunging in with 6 millimeters or whatever, full depth. That will not go with the project number 2. You got to be careful about depth of cuts. Okay, you will see some of these comments come up, and also somebody has used the high-speed machining option. No, I have not covered. It works in a very different way. It will only wreck your part quick. If in form it is tolerant, but so don't do anything that was not introduced. Okay, because it's stated in the web in some application. Don't get into it. So these are my comments. Okay, now to conclude this furnace control, this is the translated the diagram hardware you can do as a hardware, or if you want to go to the PLC, the nested logic diagram is this. Okay, P, S, F, controlling output G, and then the output S coming is coming as a result of the second round. P, not A, not F. I'll explain this in the next class. I will go through this. Okay, and then the timer. 1, 2, 3, 4, and this can be compressed into a 3 instead of 4. Okay, so 4 steps on the PLC will control this furnace control problem solution. Okay. Now, do I have another slide? Somebody. Okay, any questions? Okay, so what I am asking you to do for the project number 2, I am not asking for the report. You cannot write the report until you see your product being machined. I am looking at your Mastercam files. So out of 13 people, I have got 4 in hand. It takes a fair amount of time. I'm probably going to burn the midnight oil if I'm going to work by myself. Okay, so I will not be able to work on all 13 simultaneously. Each one probably is going to take at least a half an hour. And then are we going to cut on form and then go to the HTTP, or am I going to go straight to HTTP and let you see? Is something I'm waiting for the university's final revised schedule. Then I will do this accordingly. Your project number 2 report is probably not going to be given to me before you go on a break. Okay, I will tell you. I will look at the schedule, and if we are going till 24th, we have time to submit the project number 2 and complete it. But we'll cross the bridge when it comes to crossing. Is everything clear? Did I lose anybody? Did I mute my microphone? Or everything came out loud and clear?
Yeah, we're good.
Okay, so Tuesday group, show up at 2:30 for the lab session. I am going to be presenting project number 3 with all the bells and whistles, assumptions, animation, whatever. Okay, so see you guys in the afternoon.